In this session, we'll be solving some more numericals based on moment of inertia. But for this session, we will not be solving moment of inertia for regular geometrical sections such as square section, rectangular section, triangular section, or circular section, semicircular section, but we will be solving for sections as shown in the figure, and these sections are generally found in our RCC structures such as in beam and in columns, and they are also found in our steel structures. So if we look at the first diagram, we have a symmetrical eye section. So from the word symmetrical, it means that, as you can see in the figure, there are two flanges. Here, this is the top flange, and here it is the bottom flange. And in the middle portion, this portion here is known as a web. So, as you can see, the top flange and the bottom flange, they have the same length, which is equal to 200 mm. So, this means that this eye section here is symmetrical. It means that it has the same dimensions. So, this kind of eye sections are known as symmetrical eye sections. Now, if you look at this second diagram here, as you can see, this top flange is having its length equal to 150 mm, and if you look at this bottom flange here, its length is equal to 100 mm. So from the figure we can see that this top flange is not equal to bottom flange. The dimensions are not the same. So in this case, this kind of eye section are known as unsymmetrical eye sections, which means that the length and the dimensions of these two flanges are not equal. This is the third figure. This kind of figure is known as T-sections. And if you look at the fourth one, this is T, but it is inverted. So hence it is called as inverted T-sections. Now if you look at this diagram here, these are L sections, and if you look at the next diagram here, these are sections which looks as the alphabet C. So these are known as channel sections. Now as you can see in here, flange B and flange C, they are having the same length and hence the dimensions are also same. So this kind of channel sections are symmetrical channel sections. And if you look at this diagram here, this is also a channel section, but this is the unsymmetrical channel section, because if you look at this top flange here, which is 30 mm in length, and if you look at the bottom flange and its length is equal to 170 mm, so from here we can clearly see that the top flange and the bottom flange, they are not of the same length and hence they are not of the same dimension. So this kind of channel sections are known as unsymmetrical channel sections, and they have the shape of alphabetical letter C. So it can also be known as unsymmetrical C channel sections. If you look at this last diagram here, these are also channel sections, and as you can see, it can represent alphabetical letter U. So therefore, this is also known as U channel sections. So further in this session, we'll be finding moment of inertia of these different sections. It can either be eye section or unsymmetrical eye section. It can be T section, inverted T section, L section, channel sections, and U channel sections. Let's solve the first numerical for today's session. Let me read its statement. A symmetrical eye section of overall depth 300 mm has its flanges 150 into 10 mm and web 10 mm thick. Find the moment of inertia about its centroidal axis and axis parallel to the flanges. Also find radius of gyration and polar moment of inertia. So from the given question above, it is clear that its depth is given 300 mm here. So its overall depth given is 300 mm. Let this be its overall depth. D equals to 300 mm. And next it says flanges, which means there are two flanges. These yellow portions, both the yellow rectangles that you see here are the flanges, and its dimension is equal to 150 mm into, and its depth given is 10 mm thick. 10 mm. Now and web 10 mm thick. So this orange portion here is a web portion, and its thickness is given, this thickness is given equal to 10 mm thick, right? And we can consider consider the centroidal axis running, XX axis running from somewhere here, just an assumption, X axis, and Y axis from somewhere around here. Y axis. So now let's find number 1, moment of inertia about its centroidal axis. Centroidal axis. Now about which axis should we find when it says centroidal axis here? Because XX axis is also its centroidal axis running from XX axis, and YY axis is also a centroidal axis running from the plane YY plane. And if we look at the second condition here, it says find moment of inertia about axis parallel to its flanges. So these two flanges, flange number 1 and flange number 2, these two flanges are running parallel with this XX axis. So that means in the first condition, moment of inertia about its centroidal axis will be to find moment of inertia about IYY. So we have to find IYY is equal to, since we have two flanges here, so we do 2 into dB cube by 12 plus we have added the moment of inertia of the two flanges plus, and the remaining is this web portion in orange color. So we have only one web, so plus dB cube by 12 of web portion. So this portion here is for the flange and this portion here is for the web section. Since we have two flanges here, so I have multiplied it with 2, so we get it directly. So let us see how much we get. 2 into, how much is D? For this flange, D is equal to, depth of this flange is 10 mm. So I have 10 into B. Its width is 150 mm, and even for this second flange here, its width will be 150 mm and its depth will be 10 mm. So I have width as 150 cube divided by 12 plus. Now coming to the web portion, its depth is this depth from here till here. This is the depth of the web portion, and let us name this depth as D. Now this D will be equal to, we have to deduct the thickness of this flange, two flanges, thickness of these two flanges from the overall depth. So our overall depth is 300 and the depth of the two flanges will become 20. 10 plus 10, 20. So 300 minus 20, we get 280 mm. We have found its depth. So the depth of the web is 280 into its width. Thickness of this flange is given equal to 10 mm. So it is 10 cube by 12. So let us further solve this in a calculator. So I'll do 2 into bracket open 10 into 150 cube by 12 plus 280 into 10 raised to power 3 by 12. So the moment of inertia about the centroidal axis IYY is coming equal to 5.648. It is coming 5.648 into 10 raised to power 6 mm raised to power 4. So if we say approximately, this value can be converted. Since we have 8 here and 4 here, we can round this 4 to 5, rounding off 5.65 into 10 raised to power 6 mm raised to power 4. So this is my moment of inertia about the centroidal axis IYY. Now in the second condition, we are asked to find moment of inertia about its centroidal axis parallel to the flanges. So in number 2, we're asked to find moment of inertia about the centroidal axis parallel to the flanges. So coming back to this diagram again, if you look into the diagram, the axis which is running parallel with the two flanges is my x-axis. My x-axis here, this x-axis is running parallel with my flanges, which are flanges number 1 and flanges number 2. Now if I want to find moment of inertia about this symmetrical eye section, I can convert this symmetrical eye section into a hollow rectangular section. Imagine that this is a hollow rectangular section. Now I'm converting this symmetrical eye section into a hollow rectangular section by drawing this imaginary line and making it into a hollow rectangular section. So now let me name this section as A, B, C and D. So this A, B, C and D forms my outer rectangle, dimension of an outer rectangle, and portion, let me say that this portion here, from here, let me name this as P, and here as Q, PQ, R and S as another side, and this side again E, F, G and H, right? So I'm leaving this web portion in between here, so we are gonna deduct this web portion from in between here. So if we find moment of inertia about the centroidal axis, XX axis, we are converting this I section into a rectangular section. It will be much more easier for you to find. So let us do the numerical and let's see how we can solve this. So I come here as IXX will be equal to now moment of inertia of this outer rectangle. So moment of inertia of this outer rectangle, let me name it as moment of inertia of outer rectangle, that is rectangle A, B, C, D, minus moment of inertia of inner rectangle P, Q, R, S, or rectangle E, F, G, H. So we can take any of this and we can multiply it with 2, since we have two portions here. One hollow portion is this portion here, PQRS, and the other hollow portion is EFGH. So in between we will deduct this web portion which has thickness 10. So let us see how we can do that. So moment of inertia of outer rectangle ABCD will be equal to BD cube by 12 minus 2 into, why 2? Because we have these two hollow sections here which are PQRS and EFGH. So we have two sides, so 2 into BD cube by 12 of a inner rectangle. So let us find how much we will get this one. Let's see how much is B of this outer rectangle. The B here is equal to 150 mm. We have our B equal to 150 mm and D is equal to 300 mm. So we have for outer rectangle B is 150 and D is 300 cube by 12 minus 2. Now how much is my B? So B here, I need to take B from here till here. Only this much I need to take. So how will I find this portion here, B for inner rectangle? It will be equal to B will be equal to 150, which is the B of the outer rectangle, minus this web portion here. Thickness of web is given 10, and if I divide it by 2, so I'll be getting 150 minus 10 by 2 will be 140 by 2, which will be equal to 140 by 2 is equal to 70. So I get 70 mm. So my B is 70 mm. Now if I want to cross check it from here, if my value from here to here is 70 mm, that means from here to here will also be 70 mm. So if I add up 70 plus 10, 70 plus 10 is 80, 80 plus 70 I get exactly equals to 150 mm. So now using this value here, my B is equal to 70 into D, depth of my web portion here, is equal to 280 mm. So it is equals to 280 cube by 12. So further solving this, I get, solve in a calculator, 150 into 300 cube by 12 minus, bracket open, 2 into 70 into 280 cube by 12 will give you, I'm getting 81.39 into 10 raised to power 6. So it is coming equivalent to 81.39 into 10 raised to power 6 mm raised to power 4. So my moment of inertia about Ixx is coming 81.39 into 10 raised to power 6.
I didn't understand that.
So the next one we have, also find radius of gyration and polar moment of inertia. So let us find radius of gyration. Third one, radius of gyration. If we find radius of gyration about Ixx, it will be equal to Ixx divided by its area. Now how do you find the area of this eye section here? So let us divide these sections into 1, 2 and 3. So my area A1 will be equal to area A3, which is area of flange 1 will be equal to area of flange 3, which is equals to B into D. So my B of the, what is the B of B for my flange? It is equals to 150 and its depth is 10. So it is equal to 150 into 10. right? So it is coming equivalent to 1500 mm square. So this is my A1 and A3. Now A2, area for flange. It will be also equal to B into D, which will be equal to, how much is my B for my web portion? I'm sorry, it is not flange, web. So for my web, B is equals to 10 and its depth is equals to 280. So I have 10 into 280, I get 2800 mm square. So my total area A will be equal to area 1 plus area 2 plus area 3. So how much is my area 1? It is equals to 1500 plus area 2, 2800 plus my area 3, 1500 again. So let's add up this in a calculator. 1500 plus 2800 plus 1500. So I get 5800 as my area. 5800 mm square is my total area of the eye section. So let us find radius of gyration. Ixx will be equal to, Ixx is equal to 81.39 into 10 raised to power 6 divided by area is 5800. So let's say how much we get radius of gyration. Root over of 81.39 into 10 raised to power 6 divided by its area. So I'm getting 118.459. 118.459 mm. So approximately, if I round it off, 118.46 mm it will be. So my radius of gyration about Kxx is coming 118.46 mm. So let us find radius of gyration about radius of gyration about y axis. Kyy will be equal to root over of Iyy by its area. So how much was my moment of inertia about Iyy? Moment of inertia about Iyy was equal to 5.65 into 10 raised to power 6. So it was equal to 5.65 into 10 raised to power 6 divided by its area is 5800. So how much do we get? 5.65 into 10 raised to power 6 divided by 5800. So I'm getting 31.2. So I'm getting 31.21 mm as radius of gyration about y axis. Now the last portion they have asked us to find, polar moment of inertia. Fourth one, polar moment of inertia. So let us find polar moment of inertia IP, which is about the third axis. So to find about third axis, we have to add moment of inertia about two axes, that is Ixx and Iyy. So how much was moment of inertia about Ixx axis? It was 81.39 into 10 raised to power 6, 81.39 into 10 raised to power 6, plus moment of inertia about Iyy was equals to 5.65 into 10 raised to power 6. So adding this up, we get equal to 81.39 into 10 raised to power 6 plus 5.65 into 10 raised to power 6. So it is coming 87.04 into 10 raised to power 6. It is coming equal to 87.04 into 10 raised to power 6 mm raised to power 4. So this is your polar moment of inertia, or moment of inertia about the third plane, that is z-axis, or the z-axis, third plane, z plane is coming equal to 87.04 into 10 raised to power 6. So I hope this numerical is clear. We solved almost everything.